Hi, and welcome to week 6 of the Maths Tutor countdown to ordinary level. So the 30-week countdown on TheMathsTutor.ie. So sorry about a slight delay this morning for this lesson. It seems to be working now. We were having a bit of an issue there with the streaming service, but we should be working, hopefully. So this is week 6, and this is on area and volume. So as always, we have our couple of videos that we have for you guys. So I'm just going to pop those into the chat now. So just 1 second. So there are 2 videos that we're putting up here. So this one is about area and volume, so area and perimeter of 2D shapes. And the other one is going to be about the length of an arc and the area of a sector. So when we're dealing with these parts of area and volume this week, the 2 things that we're going to be looking at 2D shapes. So what we mean by 2-dimensional shapes is that they're going to be flat. So it means that we're not going to be looking at them in 3 dimensions. So we're going to be looking at areas and we're going to be looking at perimeters. And then in week 2 of area and volume, so the next live lesson, we'll be looking more at their volumes. So we'll be looking at how much space they take up. So the first video, as we said there, is going to be on the area and perimeter of 2D shapes. So that's popped into the chat for you now. And the second one is going to be on the length of an arc and the area of a sector. So when we're dealing with arcs and sectors, we're dealing with parts of a disc or parts of a circle. So it won't be the whole thing, but we should see. So sorry, there's still a few little technical difficulties. So I just want to copy this over and hopefully it'll pop into the stream for you now. Okay, so the second one doesn't want to copy over for me. Okay, so that second video then is going to be on the length of an arc and the area of a sector, and we're dealing again with 2D shapes. So when we're dealing with area and volume, it's very important that we have our maths tables with us and our maths tables open. So make sure you have your maths tables with you as we look at area and perimeter, mainly this week, of our 2-dimensional shapes. And we're going to see a couple of different shapes today. So some unusual ones, a little bit different. And you'll see that the pages that I'm mainly dealing with here are going to be page 8 and page 9 when I'm dealing with the shapes, because the shapes that we're going to see a couple of triangles and a couple of circles and things like that today. So they're the main pages that I'm going to be starting with. But we're going to look at a couple of exam questions that are dealing with these. So when we're dealing with these, there's a couple of things that we have to bear in mind. So when I'm dealing with the perimeter is a length. So it's a length all the way around the outside. So when it's a length, that means that we're going to have units that are something like centimeters or meters or kilometers. And it's basically imagining that we start in one point and that we're going to be walking around. Okay, so I'm just getting a message out that the first link is coming up as an error. So I'll try and get that fixed. Just a few issues this week, so bear with us. So the perimeter is going to be walking around the outside. It's going to be like a length, and we're going to have our units for length. So our kilometers, our centimeters, and our meters. When we're dealing with area, we're going to be dealing with how much space something covers. So that means that we're basically going to be dealing with two dimensions. So now we're looking at flat objects, and it might be a rectangle or a triangle or a disc. So we're going to be seeing that there's some shapes, and we're going to see how much space they're taking up. And when we're dealing with area, we're going to have meters squared, centimeters squared, kilometers squared. So we're going to have squares in our answers. And the third thing that we're going to have then are volumes. And when we're dealing with volumes, we're talking about how much space something takes up. So this time, not only is it how much space it covers, but we're also going to have either a height or a depth. So that means that we're either going to be moving upwards or downwards, and we're moving into 3 dimensions. And that means that because we're moving into 3 dimensions, we're going to have units that are cubed. So we might have meters cubed or centimeters cubed or kilometers cubed. So just to keep an eye on those things, that when we're dealing with perimeter and area and volume, we're going to have different units. And as I said, our tables are going to be so important for us. This topic comes up on both paper 1 and paper 2. So it's a bit unusual in that we can find it on both of our papers. Normally we'd say, oh, I expect to see that on paper 1, or I expect to see that on paper 2. But remember, all topics can come up on either paper, but one that we definitely find on both papers is area and volume. So we'll see this a lot. So this is a paper 1 question here, the first question, and this is from 2021, paper 1, question 8. So it says, a square sheet of cardboard of side 10 units is used to make an open box. Squares of side x units, where x is a real number, are removed from each corner of the cardboard, and it is then folded along the dotted lines as shown in the diagram below in order to create the box. So here we're starting with something that's flat, and we're going to turn it into this 3-dimensional shape. So we're turning it into this box, and it was a square. So that's important as well, because I know some of the properties of squares are that the length and the width are going to be of equal dimensions, and we're going to have right angles in the corners. But what's important is that means the lengths and the widths are going to be of equal dimensions. So if it's telling me that we have 10 across the bottom, that means that we also have a distance of 10 up along the side. But here we're going to see that we're cutting these squares out of the corners. So the squares are of side x. So that means that they have the same lengths and widths. So each of these squares in the corner that are being removed are going to have a length and a width of x. So what we have to picture now is how this flat piece of cardboard, which was a square, we're going to cut these 4 squares out of the corners, and we're going to fold it up, and we're going to turn it into our box. So the first part of this question asks us to write the length, the breadth, and the height of the box are shown in the diagram above. So write these in terms of x. So a couple of things to point out in this. In terms of x means that we'll always have x's in our answers. So when we see something is going to be in terms of x, it'll have to have x's in our answers. And there's another term there that we wouldn't see all that often. We see the length, the breadth, and the height. So the breadth is the same as the width. So sometimes they just use the term breadth, and it's given the letter B here on our diagram. So the length and the breadth are going to be the same here. So they were a distance of 10, but we're going to be subtracting an x from this side and an x from this side, which means that the length is going to become 10 minus 2x. And so will the width or the breadth, because it was a length of 10 and a width of 10, and we're subtracting 2x from either end. It means that both the length and the breadth become 10 minus 2x. So they are in terms of x because there's x's in their answers. And the height is a little bit harder to picture. When I fold up along those dotted lines and turn this into a box, the height of this is actually going to be equal to the x. So whatever the square that we're cutting out has that length of x, that's going to be our height. So we can say that the height of this is going to be in x. It also gave me my units here as 10 units. So we just keep an eye, do I need to be putting in centimeters? Do I need to put in kilometers? Do I need to put in any units? And these are just units, so I haven't got any units that I need to keep a track of as I go through this. Part B then says, show that the volume of the box can be written as this. So it's giving me an answer, and I just have to do a little bit of working to get this answer from the information that I have in part A. To work out the volume of a rectangular box, the volume is going to be the length by the breadth by the height, or the length by the width by the height. So we're going to just use our figures that we had. So our length was 10 minus 2x, our breadth was 10 minus 2x, and our height was x. So I'm going to multiply these 3 dimensions, and that's going to give me the volume of the box. So there's a little bit of algebra involved here, because I have 2 brackets and I want to multiply them, and then I want to multiply that answer by x. So it might be easier, so I know a lot of people find it easier if this x gets moved to the front, because the order doesn't matter when we're multiplying, and I'm going to say x times 10 minus 2x times 10 minus 2x. And you'll just notice that I'm taking out the multiply signs so that I don't get them mixed up with my x's. So often x's and multiplies can look very similar. So I'm just taking them out and having my brackets touching. So when I want to multiply brackets, we're going to split one of our brackets into two terms. So we split it into a 10 and a minus 2x. And both of those terms get multiplied by the second bracket, which was also 10 minus 2x. And just to remember that I still have this x at the front. So to keep that there in front, because we're going to multiply by that x as well. So we'll leave the x there for the moment and we'll multiply. So 10 by 10 gives me 100. 10 by minus 2x is minus 20x. Minus 2x by 10 is minus 20x. And minus 2x by minus 2x gives me plus 4x squared. So we're going to take this, and you can either tidy it up now or you can multiply by the x now. The order doesn't matter too much. So I'm going to multiply by the x. So I'm going to say x times 100. So that's 100x minus x times 20 is 20x is minus 20x squared. X times minus 20x is minus 20x squared again. And x times plus 4x squared is plus 4x cubed. So now we'll put like with like, so I can see that we have two x squared terms there in the center. So we're going to put those together and I'll get 100x minus 40x squared plus 4x cubed. And this is my volume, and it's the volume in terms of x. So it's a function of x, and that's why it has this v bracket x. And we're just going to rearrange it, and we're going to write it in the order that the question was. So we're going to say that's 4x cubed minus 40x squared plus 100x. And that's asking me to show that that was my answer. So I have shown my answer there. The last part that we're going to look at this question, so the last part that deals with the area and volume before it goes into a question on functions, is asking, explain why a box of height 6 units cannot be made from the sheet of cardboard. So there's a little bit of thinking involved in this one, in that I'm not using a formula here. I just need to look at, okay, if I have a height of 6 units, we had a length and a breadth. So the length and the breadth were both equal to 10 minus 2x. So if the height, which we said was x, so if the height was equal to 6, that would make the length and the breadth both equal to 10 minus 2 times 6, which is 10 minus 12, which is minus 2. So we can't have a length or a breadth that's a negative number. So all of my distances have to be positive. So the fact that we'd be getting a minus 2 for a length and a breadth means that we can't have that height. So that's all that we would need to say. Cannot have a height of 6. As length and breadth would be negative. So we can't have any value bigger than 6 either. It's just to show that they wouldn't work. So that's our first example of a question, and that's from a paper 1. Our paper 2 question, and you'll see that the tables are just starting to sneak in here at the side, whereas I didn't use the tables for the first one. I am going to use the tables here. So this 2021 paper 2 question 2b says the figure ABCD shown in the diagram consists of a large square ABCDE standing on standing on the diagonal AC of a smaller square ABCF. The smaller square has a side length of 2 centimeters. So this time I am seeing units. We have 2 centimeters. So we're just going to remember those units all the way through. And then what the question is asking me to do is to find the area and the perimeter of the figure. Okay, so my area is how much space it's covering, and our units are going to be squared. And our perimeter is going to be start at one corner and walk all the way around the outside until you get back to that position, and we're going to have a length. So we're just going to keep an eye on our units as we go through this. And what's important is what shapes that we have. So both of these are squares. So we see the square ACDE and the square ABCF. So the things that we know about squares is that the sides are going to be equal in length. So that means that ED is equal to DC is equal to AC is equal to AE. So they're equal in length. And likewise, AB is going to be equal to BC, is equal to CF, and is equal to AF. Now, it's important to see that AF and FC aren't part of my perimeter. My perimeter is going to be walking around the outside of this shape. The other thing that we know about squares is that we have right angles in the corners. So we're going to have 90 degrees in all of these right angles in our corners of our square. And that's important because to work out the lengths of the larger square, we're going to have to use the fact that we have a triangle. So I can see that down here, we have a triangle ABC. And the triangle ABC is right angled. So when we have a right angled triangle, and I know two sides of it because I know the length of AB is 2 centimeters and the length of BC is going to match that at 2 centimeters, I'm going to use Pythagoras Theorem to work out the third side. So Pythagoras Theorem, this is on page 16 of our tables. And down at the end here, we see Pythagoras Theorem says C squared is equal to A squared plus B squared. Now, you might have learned it with lots of different letters in it. They're using the letters A, B, and C because the right-angled triangle that they draw in our tables has a hypotenuse at C. So remember, the hypotenuse is always across from the right angle, and the hypotenuse here is going to be C. So we always have C squared is equal to the other two sides squared and added together. So when we look at our triangle that we have in this question here, So in this question here, I can see that the hypotenuse of this triangle is going to be this distance here, AC. So from our right-angled triangle, C squared is equal to A squared plus B squared from Pythagoras' theorem from our tables. So we're going to be saying that the length of AC to be squared is equal to the other two sides squared and added together. So the length of AC squared is going to be equal to 4 plus 4, which is going to be 8. And that means that the length of AC, we're going to find the square root of both sides, is going to be the square root of 8. So once we've worked out that that's the square root of 8, now I'm going to know all the sides of my figure. So I have the square root of 8 as this distance, the square root of 8 as this distance, the square root of 8 as this distance, and the square root of 8 as this distance. And these are all centimeters, so we have the same units all the way through, so they're going to be centimeters. So the perimeter is going to be nice and easy to work out. So now that we've worked out all of our lengths, to work out our perimeter, we start in one corner and we work adding together all the distances until we get back to that position just on the outside. So we're not going to be walking into the center of it or anything like this. The perimeter is just on the outside. So we'll see the shape that we're going to start with. We're going to start, and it doesn't matter what corner you start in. So I'm going to start up here on the top with this point here, and we're going to walk across the top, which is root 8, down, which is another root 8, and then here we're going to turn and fill in the smaller circle at the bottom, and then back up to where we started. So those pieces that we've highlighted there in purple are going to be our perimeter. So the perimeter here is going to be, so we said along the top was root 8, then from D to C was root 8, then from C to B was 2, from B to A was 2, and from A to E is root 8, and we stop. So now we're just going to add those together. So I say that's 4 plus 3 root 8. That's my answer. But I want to do something with this because the question says to give my answer for the perimeter correct to 2 decimal places. So you can just pop this straight into the calculator as it is. So all the way from the beginning, you can pop it into the calculator. And when we do that, we get an answer that says 12.48528, which is 12. So 2 decimal places, we're keeping two numbers after the decimal. The next number after those is a 5, and that tells me to round up. So I get 12.49. And because this is a perimeter, that's going to be centimeters. All right, so when it's a perimeter, we're going to have centimeters as our units. That's the first thing that we're going to work out is our perimeter. So I have my perimeter done. And the next thing that we want to work out is our area. So when we want to work out our area, we're going to come back to this shape here, and I'm just going to lift off the information that we used to work our perimeter, and I'm going to work out the area. So we have two shapes that I need to work out the area of. We have this square up at the top here, and added to that square, we have this triangle down at the bottom. So the area is going to be the area of those two things added together. So it's the area of the square, which is EDCA, plus the area of the triangle, and the triangle is ABC. So to work out the area of a square, the area of a square is going to be the length multiplied by the width. So in this case, that's going to be root 8 multiplied by root 8, which on my calculator gives me 8. And my units for area are always centimeters squared. So we're going to have our units squared, and in this case, they were centimeters, so centimeters squared. To work out the area of our triangle, there's a few different ways that we can work out the area of a triangle. And in this case, I'm going to mark that this is our right angle down here in the corner. And that means that we're going to use our formula for area of a triangle, which says a half AH. Okay, so this comes from our tables. So we'll just see that this formula is coming from our tables. And it's up here. So up here, I can see that we have our triangle on page 9, and it says the area is a half AH. And when I look at the picture to figure out what A and H are, A is going to be the base, and H is the perpendicular height. So what comes down and meets that at a right angle. So that's page 9 of our tables is where I'm getting that formula from. And we're going to use that now with our right angled triangle to work out the area for this shape. So the area of the triangle is a half the base by the perpendicular height. The base and the perpendicular height have to meet at a right angle. So we have a base and a perpendicular height meeting here in that triangle at the point B. And it doesn't matter which one that we count as the base and which one we count as the perpendicular height. So we're going to say a half multiplied by 2 multiplied by 2, and that's going to give me 2 centimeters squared. So my total area of this shape is adding those together. So I'm going to be saying 8 centimeters squared plus 2 centimeters squared. And when I add those together, I get 10 centimeters squared. So just to keep an eye on our shapes there. So we're going to see our units. So our units were centimeters squared. And we're also seeing that it said for the perimeter, give your answer correct to 2 decimal places, but it didn't say that for the area. So the fact that I got a whole number is a nice guide that I didn't have to round that off. The last question that we're going to look at today then from Area and Volume 1 is going to be from 2020 paper 2, and it's question 7 part C. So part A and B we're talking about a phone mast, but it's the part C that I wanted to look at with you in this, because this is about an unusual shape that we don't have a formula for in our tables. So it says the mast can provide a strong signal for an area in the shape of a regular hexagon of side 8 kilometers as shown in the diagram. And it says find the area of the hexagon and give your answers in. So we've got a couple of things here, kilometers squared. Sorry, so give your answers in kilometers squared and correct to 2 decimal places. So just a couple of things that we need to keep an eye on there, kilometers squared and 2 decimal places. We don't have any formula for working out an area of a hexagon, but what we can see is that when I have a distance of 8 kilometers as the radius, it means that this piece down here is also 8 kilometers. And I see that this side is also 8 kilometers. And that means that this is going to be an equilateral triangle here. So an equilateral triangle means that all 3 sides are the same, and it means that all the angles are 60 degrees. So I'm going to mark in a 60-degree angle inside that triangle there. I can also see that this hexagon is divided into 6 identical triangles like this. So each of these triangles are going to have exactly the same measurements. So it's dividing up into these 6 triangles. So when I want to work out the area, I'm going to work out the area of the triangle. And then to work out the area of the hexagon, I'm going to multiply that by 6. So we saw one formula already from our tables of working out our area of a triangle, and it said half the base by the perpendicular height. So we don't have a perpendicular height. I have no right angle in this formula, in this equilateral triangle. So we're going to look at a different formula, and this is another formula that says a half AB sine C. So this formula for working out the area of a triangle is also on page 9, and it says a half AB sine C, where we have the side A and the side B, and they meet at the angle C. So once I have 2 sides and know the angle where they meet, I'm able to use this formula instead. So we'll come back down to our hexagon, and we're going to use this formula to work out the area of the triangle, one of the triangles that makes up this hexagon. So we'll write out our formula. So our formula is a half AB sine C. And we're going to say, well, we know 2 distances that meet at an angle. So we're going to say it's a half by 8 by 8 by the sine of the angle 60. And once we have our formula and we have all that written, we can put that into our triangle, and we're going to get 16 root 3. So that's my answer that I get for the area of one of these triangles is 16 root 3. But now I want to look at my hexagon and say, well, actually we have 6 of these. So I'm going to say 6 times 16 root 3 is the area of the hexagon. So 6 times 16 root 3. And when I get that answer, I'm going to get 96 root 3. But it says correct to 2 decimal places. So I'm going to change that on my calculator, and I get 166.276. So I want 2 decimal places. So the 6 here says to round up. So I get 166.28, and my units are kilometers squared. So that's just to give you a little bit of idea of some perimeters and some areas of our 2-dimensional shapes. In our area and volume 2 next week, we're going to be looking at our 3-dimensional shapes. So we'll have our cones and our cylinders and our trapezoidal rule. But in the meantime, we have a couple of videos up there, and we'll pop them into the chat again, as I think there was some links, and apologies for the delays in getting started. So hopefully that was of some use to you.